Hi everyone, welcome to my presentation. The topic of my presentation is multi-layer network analysis of FMD transmission and containment among the battlefields. My name is Trinity. The overview of the presentation is listed here. Foot and mouth disease is a highly contagious livestock disease which can lead to destructive economic losses. Understanding the transmission dynamics of foot and mouth disease virus is very important for designing mitigation strategies. Moving infected animals and sharing contaminated equipment are the most common routes for FMD transmission, which can be described by two types of contact network, direct contact and indirect contact. Instead of focusing on a single contact network, many studies combined the direct and indirect contact network into a two-layer network. Thanks to the rapid development of communication technologies, mitigation strategies based on information sharing have been increasingly promising. However, farms' willingness to participate in the information sharing system will affect the effectiveness of information sharing mitigation strategies. To describe the FMD transmission routes by cattle movement and truck visit, we constructed a two-layer contact network based on the movement data. On top of the contact network, we added an information sharing layer to simulate the influence of different information sharing networks and the participation rate in suppressing the epidemic. Figure 1 shows the three-layer network. The nodes linked by the dashed line between different layers represent the same farms. The edges within the same layer represents the contacts. In our work, these three layers stands for information sharing layer, indirect contact layer, and direct contact layer. The direct contact layer models the cattle movements between farms. Each cattle movement is generated as a directed edges from the departure farm pointing to the destination ones. The indirect contact layer models the track sharing. The farms are connected in the indirect contact layer if they are visited by the same track in the same week. The pathogens can transmit it through these two layers at different rates. The information sharing layer is used by the participated farms to inform their neighbors of their infection states. In this work, we used an SQEIR disease model. SQEIR model categorizes the hosts as susceptible, quarantined, exposed, infectious, and removed. The susceptible are individuals only exposed to the pathogen. Exposed are populations that are infected but not yet infectious. Infectious individuals can infect the susceptible by contacts. The removed are populations who clear the infection by hospitalization, death, and quarantine measures. A susceptible node can be quarantined if it receives notification from infectious neighboring farms in the information sharing layer. The state transition process is expressed in these equations. We designed two sets of simulations to explore the impact of cattle movement, track visits, and information sharing on disease spreading and the impact of different information sharing layers and premises participation on disease spreading. First, we simulate the hypothetic FMD spreading on the single layer networks, two-layer networks, and three-layer networks. Then three different types of the information sharing layer are added individually to the contact networks. In each information sharing network, we randomly activate 10% to 100% participation nodes and deactivate the rest. The number of farms in different infection compartments are shown in these figures. Our results show that the track visit layer prolongs the epidemic duration and enlarges the overall epidemic size. The random information sharing layer mitigates the epidemics by shortening the duration and suppressing the epidemic size. Figure 5 and Figure 6 shows the maximum and average of the epidemic size and quarantine size versus participation levels when different information sharing layers are applied. In general, the epidemic size decreases and the quarantine size increases when more farms participated in the information sharing networks. The maximum and average epidemic size of the contact-based information sharing layer is the smallest among the other information sharing layers, which means the contact-based information sharing layer has the best performance on containing the disease spread. The contributions of this work includes revealing the track visits can prolong the epidemic duration and enlarge the epidemic size. The information sharing network is tested to be useful and effective for epidemic mitigation. The increasing participation of the information sharing network reduces the epidemic size. The contact-based network performs the best on suppressing the epidemic size while maintaining a low quarantine size. This work was supported by the National Science Foundation. Also, the following professors give us plenty of supports and guidance. We really appreciate it. Thanks for your patience.